It's another math day here with teacher Jenny. Join me for another topic. This time we're going to talk about the second part of the video on limits at infinity, wherein you will be encountering polynomial with a mixture of rational functions. So let's have this one here. First example, we've got the limit of 3 over x to the power 5 as your x approaches positive infinity. So we have a theorem for this one in which once you've got a limit of your 1 over x to the power of r as your x approaches positive infinity or a negative infinity, that will give off a 0 as the value. Because the reason here is once you try to extend or if this one becomes bigger and bigger in value, that will be moving closer and closer to a value which is 0. So you can try it out. You can have it 1 over 1,000. What will be the result for that one? That will be a 0.001. And once you've got there a 1 over 10,000, that will become a 0.001. So as you can see, it's moving closer to a 0. So that means to say that once you get the limit of your 1 over a bigger number, that will be moving closer to a 0 as the value. So the limit there is a 0. I mean, that's with a 0 there. So let's now go back to our example. So once you've got their limit of 3 over x to the power 5 as your x approaches positive infinity, we'll be applying this concept here or the theorem here, in which once you try to evaluate this, we can take out 3 as our common multiple here. So taking out 3, and then we've got the limit of your 1 over x to the power of 5, because once you try to take out 3 as a common multiple, that would simply mean that we are left with a 1 in here because we took out 3. This is similar to as when you say 3 times 1 over x to the power of 5, in which once we multiply a whole number with a fraction, automatically we just have to multiply the numerator and then we copy the denominator because we've got a 1 here. So multiplying 3 and 1 and then 1 and x to the power 5, that will give off a 3 over x to the power 5. So that is what we had on the original given. So once we try to evaluate the limit there, we wish to come up with a format of your limit of 1 over x to the power of something as your x approaches to a positive infinity, because out from here, no matter what will be your exponent here, that will always be equal to the entire thing. The entire limit here will always be equal to a 0. And no matter what is the sign of your infinity here, that will always be the limit, which is a 0. So this is now 3 times. This entire limit here is a 0. So 3 times 0 is a 0. So the limit of 3 over x to the power 5 as your x approaches positive infinity is a 0. Another example here is the limit of 1 minus 2 over x plus 5 over 3 x to the power of 4. So first we can try to separate or apply the limit laws for sum and difference. So we can have it as the limit of the first term is 1 as your x approaches negative infinity minus limit of the second term, which is 2 over x as your x approaches negative infinity, and then plus limit of 5 over 3x to the power 4 as your x approaches negative infinity. So here we've got limit of a constant is still a constant, which is 1. And then we've got limit of 2 over x. We can simply detach 2 out from there because that's common multiple. So we can have 2 times the limit of 1 over x as your x approaches negative infinity. And then plus detaching again 5 there because that's common multiple. So we have 5 times the limit of 1 over 3x to the power 4 as your x approaches negative infinity. Now, you can have it like this, or you can just simply look at it and then evaluate each of those terms, and then you will have the final answer. That's really fine. So this is now 1 minus 2. The limit of 1 over x as your x approaches negative infinity is a 0. And then we have plus 5 times the limit of this one is also a 0. Because if you try to have it as 1 over x, the 1 over x there is simply a 0. So everything will become a 0 here. So times a 0. And then we have that as 1 because this one will become a 0 while this one also becomes a 0. So we've got the limit of that one is equal to a 1. We have the limit of 5x minus 2 over x plus 3 as your x approaches negative infinity. So we can simply separate that one as the limit of 5x as your x approaches negative infinity minus the limit of 2 over x plus 3 as your x approaches to a negative infinity. So for this one, we can have it as the limit or evaluating that one. So we've got 5 out, and then we have the limit of x as your x approaches negative infinity. You may do the direct substitution for that one. It's really fine. And then we have to take out 2 here, and then we've got the limit of 1 over x plus 3 as your x approaches negative infinity. This one is 5, and then limit of x, that will be as x approaches negative infinity is a negative infinity. And then minus 2. For this one, we've got a problem for that one because we have an x plus 3 in here. We cannot go directly as to jump that will be equivalent to a 0. But we have to prove that should be a 0 by simply getting the highest exponent here on the fraction or the denominator, the highest exponent variable here. We have to multiply the entire thing with 1 over the highest exponent variable. So it's gonna be like this, 1 over x plus 3. We will be multiplying that one, the top and the bottom, with, since this is with x to the power of 1, that's the highest exponent variable there. So we have to multiply each of the position, the numerator and denominator, by 1 over x. And also here as 1 over x. As your x approaches negative infinity. So here we can simplify this one. This is a negative infinity because we have positive 5 times negative infinity. That's a negative infinity still. And then minus 2, we've got the limit of 1 times 1 over x. That's 1 over x. Over, we've got here x times 1 over x. So we have x times 1 over x. X here is it with 1 as a denominator. So x times 1, that is an x. And then 1 times x, that is also an x. So this is equal to a 1. So at the bottom part, we've got 1 here plus. We have a 3 times 1 over x. That will be 3 with a 1. So 3 times 1 is 3. 1 times x is x. So this will be with 3 over x as your x approaches negative infinity. So this is now negative infinity minus 2. We will be evaluating each of this. So we'll be applying limit for each of our positions. So we have here 2 times the limit of 1 over x at the top as your x approaches negative infinity over the limit of 1 plus 3 over x as your x approaches negative infinity at the bottom part. And then we try to simplify that one. This is now equal to negative infinity minus 2. And then we evaluate the top. This one is a 0. So 0 will be at the top, and at the bottom part, we've got here limit of 1 as your x approaches negative infinity plus the limit of 3 over x as your x approaches negative infinity. And then we try to simplify that one. So negative infinity minus 2. We've got a 0 at the top over limit of 1 is 1. Limit of 3 over x as x approaches negative infinity is a 0. So simplifying that, we have negative infinity minus 2. We've got a 0 over 1. This is equal to a 0. So we have negative infinity minus 2 times 0. And then this is negative infinity minus 0. That's a negative infinity. So the answer for that one is a negative infinity. So another scenario here is like this. You've got a limit of 3x minus 2 over an x as your x approaches negative infinity. Actually, you can simplify this one. You can break this one apart because we've got a monomial or one-term denominator. So you can have it as the limit of 3x over x minus 2 over x. So notice I've separated a 1 with our x as the denominator of each of the terms at the top here. So once you try to put it back, take note they have the same denominator. So most likely we're just combining the top here. So 3x minus 2, that is still the same function. And then as your x approaches positive infinity. So the reason here why we try to separate that one is that we can come up with a look in which we can have a satisfaction on the theorem that we've learned about the limit of infinity or at infinity, wherein you have 1 over an x to the power of something that would lead to a 0. So this is now equal to limit of, this one will be canceled and that one. So we've got the limit of 3. If we try to distribute our limit to the two terms, so limit of 3 as your x approaches positive infinity minus the limit of 2 over x as your x approaches positive infinity. So limit of 3, that's 3. Limit of a constant is a constant. And then minus, we've got limit of 2 over x. We can simply get the 2 out because that's a common multiple. And then we are left with limit of 1 over x as your x approaches a positive infinity. This would lead to a 0. So we have here 3 minus 2 times 0. 2 times 0 is a 0. So this is now equivalent to a 3. And lastly, we have this one. So we have limit of negative 5x cubed minus 2x plus 4 over x to the power of 4. We can simply break that apart as your x approaches a negative infinity. We can try to break it apart and have a single term each of this and then apply the limit, like having this one as the limit of negative 5x cubed over the x to the power 4. So we're just simply getting each of the term at the top and then having the denominator as the denominator here. And then we have minus 2x over x to the power 4. Then we have a plus here. And then 4 over x to the power 4. So that once you wanted to put it back, you still have the same function that you've got there. So as your x approaches negative infinity. So evaluating each, we have now the limit of negative 5x cubed over x to the power 4 as your x approaches negative infinity minus the limit of 2x over x to the power 4 as your x approaches negative infinity plus your limit of 4 over x to the power 4 as your x approaches negative infinity. So simplifying that one, we have here limit of x cubed over x to the power 4. If you've got an x cubed here, you can actually have the x cubed equivalent to an x times x times x. So that's x cubed. When you say over x to the power 4, we have it as x times x times x times x. So we are actually canceling those that are the same. So we have that one, which is left. So we have that as a 1. We don't have an x anymore at the top, but we do have an x at the bottom part. So that's 1 over x. So having that 1, we still have a negative 5 here. Negative 5 times 1, that's a negative 5 over x. And then we have x approaches negative infinity. And then we have here minus. We are going to simplify this one again. So we have here a 2x. So we just have to copy the 2 there. So limit of 2. And then we've got an x, only one x. And then x to the power 4. This would simply mean that we have an x over x times x times x times x. Cancel that one. We have 1 over x cubed. Or simply, this is with 1 here. Once you do 1 minus 4, that's a negative 3. Since that's negative, that will be placed at the bottom part or the denominator part so that your exponent will become a positive. So this is now 1 times 2, that's 1. So we have 2 over x to the power of 3 as your x approaches negative infinity. We have plus. We've got a 4 here. We can take it out so that we can have limit of 1 over x to the power 4 as your x approaches negative infinity. Then simplifying, we take out negative 5 here because it's a common factor. Multiple. So we have negative 5 limit. And then once we take out negative 5, we are left with 1 here over x as your x approaches negative infinity. And then we have minus. We take out 2 as a common multiple. And a limit of 1 over x cubed as your x approaches negative infinity. And then plus 4 times the limit of this one, that is a 0. And then we evaluate. This is negative 5. The limit of that one is a 0. Minus 2. The limit of this is a 0. And then plus 4 times 0 is 0. Everything here will become a 0. So the limit of this one is a 0. So that's it. That's the second part of the video on limits at infinity. So please stay tuned for the limits at infinity video number 3 because there's a shortcut for this type of function, the rational function. So I hope you stay tuned and do like the video and share. And please subscribe.